questions about last time? Okay, so we have been talking about statements and the relation of the algebra of logic of statements to the algebra of sets. So we'll talk about sets more soon, but there is more here to talk about. And one thing that I skipped by mistake is the truth table, the truth tables, and I covered almost all of them with one exception. So we did over here, we did the truth table of the and and or. Okay, the truth table of the negative is very simple. It's somewhere else, and this is the truth of the contrapositive, which is the same. And the one thing that is also needs to be mentioned is the truth table of the implication is also very simple, but still needs to be mentioned. So what I'm talking about is that if A implies B, what about the relation between the truth of the one and the other? Okay, so if I have A and B here, so if A is true, is B true or false?
It depends, right? Oh, wait, I have no clue, to be honest.
No, so anybody has an idea? What? Yes, it is. Can you explain?
It's like an if then, so if A is true, then that implies that B is true.
Right. So that is the definition of the implication, right? So it is exactly so. If A is true, then B has true. So that is a literal translation. If A is true, then B is true. Okay, so that goes both ways. That's exactly the same thing. Okay, what if A is false?
And B is false?
No.
It could be either.
Is it true? Could be either, right? So it all depends. So as you look at the meaning of our implication right there on the left, and you cannot reverse it. You cannot reverse it. You cannot say anything about whatever. If A is not true, so we cannot conclude anything from a fact that is not on the list. So if A is not true, then there is no conclusion to be drawn about B. I guess an example would be so how about divisible numbers? So say x is divisible by 4, then that's A. Okay, and then x is divisible by 2. Right? If it's divisible by 4, then it's divisible by 2. So certainly the statement A could be untrue, but if it is true, then the second one is true too. So whatever values of x value of x is, the truthfulness will translate from A to B. But we certainly can pick a number. There is a number. How about 6, which will for which A is true but B is not, and you certainly can think and vice versa. So 8 is both are true, and here for 6, what is it? A is false, B true. Okay, so as you can see, so that's an example of testing of your ability to draw conclusions. If it fails in one example, as here, then well, you know that that conclusion is incorrect. And in fact, everything is a statement. So I was talking about two statements. What if I look at this together? It's also a statement. Say C. Right? So we're saying that if x is divisible by 4, then x is divisible by 2, and we can say then that, well, as stated, C is true, but its converse is not. Okay, so in general, it's the same thing. I could say C. This one could be a statement. Okay, so this brings us to the important development here. It is that our statements are actually just came up. Parameter dependent. So if we're talking about a number, then whether the statement is true or false depends on that number. Okay, so the number could be even or not. So depending on x, if my statement is x is even, say true false, and the answer is depends on x. Right? So if this is my statement, a is equal to, there is no standard notation for how to put the statements in parentheses or something like that. I'll put them in just in boxes for the time being. So so the statement A is x is even, and I cannot really ask myself what is it true or false because it depends on x. So what's the way out? The way out is to literally have x to be present as a parameter. So this like this, a of x is even. It looks like function, right? But really it is. In a sense, it is. In a sense, it is a function. So x being an integer here, it's like the input. Input a number. Well, specifically here it will be an integer. What's the output? No. So remember how functions operate. There is an input, which could be a number, could be anything, or abstract quantity or quality. That doesn't matter whatsoever. And then for each input there is an output. So depending on x, we're going to produce what kind of outputs? True or false, exactly. So the output is pretty much two letters, T and F, or also known as in some other fields 0 and 1. So 1 for true and 0 for false. So that reveals that idea reveals more algebra behind logic. So because some of the combinations will be so let's look at this. Say we could talk about the statements if or then. If this is or, right? And I could also talk about B with and. Okay, but then remember A and B are statements depending on x. These two statements might be true or false. And if we just look at our truth tables for these. So I put here A and B, and true. How about instead of true false, I put 0 and 1. Okay, so let's do 0, 1. So 0 is false, 1 true, 0, 1 false. So when both are false, what about and? This is say C. Okay, so what are the answers here? 0 and 0 gives me what? 0, 0 and 1, 1, 1 and 1. Okay, so that pretty much is my it is a truth table, but expressed with numbers, and you can probably try to guess what kind of algebra we have behind it. So, well, let's. Do you see any patterns here? So 0 and 0 gives me 0. 0 and 1 gives me 1. 1 and 0 is also 1, but 1 and 1 is also gives me 1. Anything? Does it remind you of anything? Well, maybe not. But let's do the other one. A and B, when we go and 0, 1, 0, 1, both of them are false. Is 0, right? And then and we have ones here. The truth table is true. I'm sorry. No, this is 0 like this. Okay. So if one of them is false, then then C is false too. Okay. So well, this one you can actually guess what the operation is. It is just multiplication. Yes, this is just multiplication. So whenever you have the only two numbers that you have 0 and 1, you can actually carry out multiplication and still getting only zeros and ones, and that is the truth false logic that of statements with these in these truth tables. Okay, so that, and then can you guess what's happening with the first one? So it's certainly not multiplication. What? It's not subtraction either. So, right. No, it is addition. So there is no familiar operation here. So we are facing now, and we'll face more of some weird algebraic operations that we'll have to investigate soon enough. But at least one of them is very easily seen to be literally multiplication. So a way to remember. Okay, so back to these functions. So true, false is, or 0, 1. They only need two outputs. The x could be, for example, a number. If we're talking about numbers, then the input is a number, but the output is 0 or 1, true or false. Okay, so they're kind of functions, and they kind of combine in this manner. For example, they can combine with these two, and they, in fact, they could be even, you can even form compositions if you want. Okay, so let's see. Okay, so that's the how the parameter how notation that we use. So let's make a few statements. So for example, a of 2 is true or 1. A 1 is false. Okay, so there you go. Okay, how about this one? A of okay, here we go. X plus Y. No, we don't know. It still depends on X and Y. But the point being is that we talked about that just recently, remember? The very first statement on Monday, we talked about the sum of two even numbers is even, remember? So can we use that, at least in part, to make a meaningful computation? So this is what I'm talking about. If we know some about evenness of x and evenness of y, what can we say about the evenness of their sum? Right, so in other words, if this is 1 and this is 1, then this is 1 too, right? Okay, what? It is an end. Is it? This one works out, but what if, so then, okay, if we continue on, 0, 1, 1, so 1 odd, 1 even gives me 0, 1, 0 gives me still 0, but then there is the third option, 0 and 0. What does it give me? Yeah, so it gives me 1 once again, right? So that is not that's the whole computation is right here, but how those zeros and ones on the right rather, combine to get the number on left is not the same as what we see over there. So as you can see, false gives me true, because of the specific nature of the problem. It's about evenness, so it just happens that two odd numbers, that's what the last line is. Two odd numbers added together give me an even number. Okay, so odd plus odd is even. That's what it says. So this one is, what is it? Even plus odd is equal to odd. Odd plus even is even. Odd. And even gives me even. Okay. So they're combined in a more complex way. So 1 plus 1 times 1 is 1, but 0 times 0, whatever the operation is, it remains unclear for the time being. But that certainly is something for us to continue to investigate. Let's look at some of the statements that we have seen, and we realize that the statement as is, it depends on X, but there's always, often, there is what we say a preamble. Of a statement. So before we get to this AX, say AX is once again, X is even. We also might, to form this statement that would be independent of X, would have to make we would have to put quantifiers on the statement. Let me actually pick a different statement here. So let's do what we did before. X is an economics major. So in other words, we're talking about students. So so let's remember what we talked about. That statement's also from Monday. The statement was let's call it C. Every student in this room is an economics major. Okay, so let's see. As you can see, C is not a parameter dependent. It is a absolute statement about every student in the room. So there is no dependency. You won't. So it depends on something. It does not depend on anything. It is what it is. So let's express C in terms of A. There, you see?
Would it be X is in this room?
X is in the, so remember, first of all, let's remember that there was what we did on Monday was we stated this C statement as an implication. Remember, so if the student is in this room, then he is an economics major. Okay, so that's one way. We are pursuing slightly different angle here, and then we have to proceed to we have to put something to restrict our attention on the x's. So indeed, X is a student in this room. Has to be a student in this room, but the crucial word here is every. So this is how we would start moving in that direction. I would say C is equal to, the statement is, well, here it is, for every student in this room, that's the preamble. And that's the actual statement. Maybe comma here if you like. So once again, read it. C as I just written. And what do you end up with is, for every student in this room, X is an economics major, right? For every student X in this room, I'm sorry, that would be a proper way to put it. For every student X in the room, A of X is true. And what is A of X? Is X is an economics major. Okay, so so as you can see, there's no implication this time, and we are more talking about imposing these extra conditions in the beginning of the statements of the statement. So for every, this is the for every, for any, and for each, and for all. All of these words are good, and so we. Which one is better is hard to tell. Which one do you prefer to make that point? So you know what we're talking about. Which word do you think is best appropriate here? That's just personal choice, but I'm just wondering. So it's obviously they're all true, right? So all students in this room are all I guess is now all is not as applicable anymore because we're talking to one student at a time. That's why we chose X is an economics major. But otherwise, every, any, or each is all these words are appropriate. And which one? Sometimes the any sometimes sounds, at least in my experience, sometimes any might be misunderstood as it's you pick a random one, and or a random or pick one, and that's it. So. But it's not an any. It is in mathematical context. Any means all. It means every and each. So we test every student in the room and verify whether he or she is a economics major. Okay. So then the well, I'm just wondering if you remember where you saw this construction previously in maybe calculus. So it's always written in a casual language, but very frequently the theorems start with this language for every number, for every function, for every sequence, and so on, or every integral or something like that, or for every triangle, for every right triangle. Theorems start in that fashion. Okay, and well, there's a symbol for it. Have you seen this before? So that is it's called a quantifier. There will be just two. This quantifier is literally translated as for each x. So the as it is normally explained, is supposed to stand for it is a upside down. So either all or any, you take that letter in the beginning of that letter and turn it upside down, you have this symbol. It is then it is read as for every or for any x. Okay, so then C becomes this for every x, A of x. Okay. So we're not going to overdo this. It is no more than just a tool, and a lot of, or just about, if you open a textbook, they hardly ever use these symbols. It's usually a tool for you to take a statement apart, and so look at how the different parts of the statement relate to each other, so that you are perfectly clear about the logic of the statement. We certainly start with these very simple ones. And so we have, it could be every student is a math major or economics major, or every number is an even number, or every number within this set is an even number. Sometimes, as you can see, sometimes over here it's not purely just for any, but sometimes some things are tucked in here, extra restrictions on X. So for example, here we have an extra restriction. It is in this room. So that extra restriction would appear following X before you get to the statement. So sometimes this preamble becomes quite long. Actually, it's considered bad form to make it too long, because you can always turn this one into an implication, and to say that if X is in this room, then it is an economics major. But logic is it is a good idea to have different ways to state something like that. So let's use the what we just saw a minute ago. This one. So these are, well, this is we have talked about the first one, and we did not discuss the rest of them. These statements about how odd and even numbers added together produce odd or even numbers. Is it clear? Do we need to talk about why this is true? These three statements. Odd plus even. Why is it odd? What? Well, that's not good enough anymore, right? So just remember we spent quite a bit of time on the first one over here. And it was, we did analysis. It took a page, and then half a page the proof itself. So I don't want to do it from scratch, but at least what is the core? Say, let's look at the second line over here. So what is the essence of the proof? Right. Well, let me just maybe take you all the way back and to that theorem, and looking at straight at the proof. This is the proof that the sum of two even numbers is even. I circled in the middle the core of the proof. Okay. So now suppose we're trying to do something else with this theorem, but we're talking about A and B not being both even, but suppose both of the one of them is even and the other one is odd. Yeah.
An odd number wouldn't be like 2m, it should be n, it should be some integer. It's not divisible by
It will be to say B is odd, say, well, let me be correct here, odd. Then if B is odd, it will be 2m plus 1. Okay? Now you see what's going to happen then. A plus B will be 2n plus 2m plus 1 plus 1. Right? Let me erase this. Okay, so can you now, so anybody can read the proof now? So what we're trying to prove here is that the sum of one number that is odd and the other one is even, or vice versa rather, then the sum is also odd. Okay, so the sum of an even number and an odd number is odd. Okay. Well, maybe I should have just copied it. Come on. Okay, so let me just copy this. Okay. Where's the copy? Where's copy? Use this old-fashioned way. Okay, so we gotta put this out and get it out of the way. Paste. Okay, so let's fix it. Let's fix it, and of an odd number, an even number, and an odd number is odd. Okay, so we started doing this. So suppose A and B are integers. Since A is even, A is equal to 2n for some integer n. We know that already. Now what we know about odd numbers is that well, what is definition of odd? It's the number that's not even, which means that it is not divisible by 2, which means that it has this extra plus 1 over here. Right? So that's what makes a number not divisible by 2 if it is divisible by 2 number plus 1. So an odd number is a number that is even plus 1, okay, or minus 1. Doesn't matter. Okay, so it's 2n plus 1 for some integer m. Now we consider the sum, 2n plus 2m plus 1. Just to make it even more explicit, I could put parentheses here. So like this is the first, this is A, and this is B. Okay, and then I remove the parentheses and rearrange the terms, and that's extra 1 term appears here. And now just simply by examination, we realize that the number on the right is what? Odd, right. Right, because n plus m is an integer as the sum of two integers, so a plus 2 plus a is odd. Okay, so if you put some effort into a proof, then there are always ways to produce more proofs from it, if it's just done carefully. So yes, you see we demonstrated that even plus odd is odd. Well, odd plus even is also odd. How do we justify that? Just flip it, and finally odd plus odd. I'll let you think about it at home. About once again take this proof and do odd plus odd is even. Okay, so think about that. And in the meantime, what I'm going to do is I wanted to make these 4 statements over here. I want to put them in the in the form of logical statements. So we have only one statement, a of x, which is right here. A of x, it means x is even. Okay, so let's start over. Okay, so the first statement is even plus even is even. Okay, so the statement is a of x is x is even. Okay, so let's translate this into the language using the statement a. So two numbers a and b. Okay. Okay. So what should I start with? A, b, a plus b. Okay, maybe let's start slowly. Okay, so let me write it out. If, or rather, let's do it for any a even and any b even, a plus b is even. Okay? So now then a appears. How many times the a statement at the top, how many times does it appear? Three times. How many does even appear? So a is even, b is even, a plus b is even. Okay, so let me just then take it and put it in the form of. So the first circle is a, right? That's first circle. A is even is now translated as a. It is exactly what it says. A of a. Okay, this is a b. Okay, and finally a plus b. So these are the three statements now have been translated into the language of a. What remains is simply to say that to missing parts, to take care of the missing parts over here. So let's do an implication. I think it will be slightly easier. Okay, so let's say if a is even and b is even, then a plus b is even. Okay, so how do we translate these three words into symbols? Filling these missing parts. Maybe. So now let's start with and. What happens to the end?
Turns into a carrot.
Yeah, the upside down V. Okay. Anything else?
The first one will be the upside down A.
No. I changed my mind and decided to do the implication. So the implication is, as you can see, there's no for any anymore. So so then we are talking about an implication. So where do I put the implication symbol? Right here. So this is how you formalize a statement which is even plus even is even, very informal, quick, and easy to remember, understand statement over here we started with, and then we put it, we translate it into this. So let me put it together. A and AB implies that A plus B. Okay? So we already know everything there is to say. Now there are two more statements. Even plus odd is, so I'm sorry, that's, so the next one, so this number one. Number two, even plus odd.
On that number one, how do you know that the numbers are even if you're not given the sentence up there and you got the short version right there?
Now, I'm sure you're talking about the new one or the...
The new one with
Yeah.
just the symbols, like how do you know it's even
It-
without looking up at the sentence up there, or you just gotta look up there to see the sentence?
I have to know what A is. That's all, right? it is the statement and end up to be dependent on A and B. So I once again I put that away for a moment at least, so that we will sort this out first. But so it's all dependent on A and B. But other than that, this is a statement about A and B. In terms of A, statement A capital A over here, so if you just read it,
Yeah.
it is like what is it, like a dictionary, and you just look at it and you translate it. So as long as you know what A is, you can have it. So anyway, even plus odd is odd. Let's write a similar formula. Can you write it right away? Even plus odd is odd. So this is what we're looking at, is even plus even is even.
So is it just A,
Yeah.
for the next one, do you put A, B plus 1?
No, we don't do we don't add 1 to a statement, because this is a number.
Okay.
So a relation between A, or rather B is odd, B is even. What's the relation between these two statements? Negation, yeah. So this is what I do. It's still and, right? And AB bar. So that's, in other words, I'm rather than saying it's odd, I'm saying it's not even.
Okay.
Okay. And what do I have on the right? Same story.
Just A of A plus B with a bar.
Yes. Okay, so same for number 3, even plus odd. And now on number 4 is odd plus odd.
So kind of with all these, you're comparing it to like the first statement that you made, where it's,
Yeah.
you're saying.
Well, I mean, I only do it so we would skip these steps.
Okay.
If you already feel that you can do it, then you skip the steps and just write it out if you see it. Even if you don't, certainly backwards, it is much easier to understand rather than from words to formulas, more harder than from formulas to words. So odd plus odd, okay, just tell me what to do. AA bar, no bar. It is even, right? Okay, so I want to take a look at the last one and look at it one more time, and there is a way to restate it. There is a way to restate it. So odd plus odd is even. Let's look at the formula. Odd, the first number is odd, and the second number is odd. No, wait a minute. Which one am I looking at? No, let's look at number 2. This one. So the first number is even, and the second one is not odd. Well, what I'm trying to do, I'm trying to, since we used and in all 3 of these examples, can I use or?
Make them both not even. Say A of A bar or A of B.
Well, actually, maybe no, but it seems the answer is no. But I just wonder if you can see what. Can we make anything from this? That's the question. So when one is odd and the other one is even, then the number is the output A plus B is odd. What if I put or there instead of and? Can we say anything about the conclusion? So in other words, so this statement, can you translate this statement that I already have in plain language?
New one or
The new one, yes.
A is even or B is not even?
Right. is even, okay, A is even or B is not even. Yeah, there is really nothing. A is even or B is not even. I don't think we can draw any conclusions from that. Okay, how about this? What if, so there is nothing useful here. What about this one? Either one is even or the other is even. No. No. What should I put here? When you take two numbers and both of them are, or one of them is even. I'm wondering if you can see a new theorem here. It is or, but how do you combine two numbers? One of them is even to produce an even number. It's or you multiply. Oh, so it's AB. AB is even then, right? If at least one of the two numbers is even, then the product is even. Okay, so that's how a very compact way to put it. And so there are a bunch of theorems that you can discover about it, and this is what number theory is all about, except usually it is not just odd and even, which is all entirely about divisibility by 2, but rather we also look at divisibility by all numbers, and we'll look into that shortly. At this time, I wanna take this to the and go back to preamble. Preamble. So as you can see here, it is I omitted that part, and sometimes it's when it's obvious what I'm talking about. You say we're talking about integers, then there is no need for that. But also sometimes it's a good idea. So for example, if I look at the very first one, I would say for any A and for any B, that would be a complete statement. A B implies A plus B. Okay, so that would be a complete statement rather than the preamble is omitted. So I copied this one. I just took this and copied it, but I added the preamble. Okay, so there is the second. There is the other quantifier of that we could be in the preamble is the res. The res. So this is for any, and this one is the res. There is or there exists. Okay, so for any, like I said, it's just about every theorem. In mathematics starts with for any number, for any function, and so on. But sometimes some theorem, not as often, they start with the res. They are less typical, but still it's still possible. An example would be, for example, there is a function that's not continuous. Okay, or there is a well, how about this? X squared, there is an x such that x squared is equal to 1. Okay? So it tells you where that, for example, that particular equation has a solution. There is a solution. So even though this one has 2, keep that in mind. We say there is, but it doesn't mean that there is only 1. It might be many. So x squared equal 1. There is 2 solutions. But all we're saying is just this general statement about that condition does not have to be satisfied every time. What am I saying there? Yeah?
So would that be saying there is an x such that x is even?
No. You mean the last line? Yes. There is an even number. That's all there is here. There are, if you prefer. It doesn't really matter. There are even numbers, right? So there are even numbers. That's what we're saying. This is certainly is a statement that is not interesting. Let me put it. Let me do a combination which is slightly more interesting. How about this? For any A, there is a B such that A plus B. How about that? Can you translate this? Yeah?
For any A, there is a B such that that satisfies A of A plus B.
Right, but which is that their sum is even. So for any number, there is you can add to it another number which makes the sum even. True or false? True, right. If it's even, you pick an even. If it's odd, pick an odd, and that's how you have the answer. So once again, this is the preamble. You saw this preamble in Calculus 1, remember? Something like that. There is, for any A, there is a B. Remember this? No, I'm trying to remind you of a particular definition from Calculus 1. The limit definition, which starts with, for any epsilon greater than 0, there is a delta greater than 0, such that, and then followed by the statement. So as you can see, this is the preamble first, for any, second, there is, and then followed by, and in fact, an implication, x minus a less than delta implies that f of x minus l is less than epsilon. Okay, so at this point, whenever, it was my experience, I remember reading this for the first time, it was very hard to understand, even though it is just two lines of text. So decomposing it in this fashion, as we just saw, certainly helps, and that is why it is such an important tool in mathematics. Okay, so we'll continue next week. So once again, make sure that you can log in